Okay, so what happens if we increase the light brightness without changing frequency? So if we're not going to change the frequency, then that means that we need to be using the same type of photon the whole time. So I'm going to use violet visible photons the whole time. So I've got dim violet light, and that is coming in and it's hitting a piece of metal. This blue thing right here, this is the piece of metal. And let's say that we're above the threshold frequency, so electrons are released from the metal. Now we repeat this. We're still using violet light, but this time it's bright violet light. So we've increased the brightness, or also known as increasing the intensity, and that violet light's hitting a metal, and we're still above the threshold frequency, so we're releasing electrons from the metal. What is the difference between these two situations? Well, in this one, where the light is brighter, we're going to have more electrons being released. And so the reason for that is because if you use more intense light, that light contains more photons, and since each photon releases one electron, you're going to get more electrons being released. So we're going to get more electrons flowing through the circuit. The thing is, though, okay, the photocurrent will increase. So photocurrent is just current, okay, and photocurrent depends on number of electrons. That's all it depends on. So if you have more electrons, you're going to have more photocurrent, okay? However, changing the brightness or the intensity of the light does not change the kinetic energy or the speed of the electrons. And this is because brightness has nothing to do with energy. Remember, they're two separate concepts. Okay, now let's kind of do the opposite. So what happens if we increase the light frequency without changing the intensity? So first we're going to start with red visible light, and then we're going to change it to violet visible light. And let's have a look at what happens. So we can actually use our conservation of energy formula from earlier to help us think about this. So red photons have approximately 1.5 electron volts of energy, and violet photons carry approximately 3 electron volts of energy. Now let's say that it's the same setup, right, with the red light as it is for the violet light. So the work function of the metal is going to be the same in both cases. Just to keep it simple, I'm going to say that we're using a metal with 1 electron volt of energy. Well, whatever amount is left over is going to be the kinetic energy. So here, okay, this amount that I'm boxing off, that's the leftover amount. That's what becomes kinetic energy of the electrons. So we're going to have half an electron volt left over for the red light, but we're going to have 2 electron volts left over for the violet light. So what's happening here is that the electrons that are being released by the violet light have more kinetic energy, and therefore they're going to be moving faster. So the electrons move faster for the violet light since they have more kinetic energy. However, the photocurrent does not change, and that's again because photocurrent depends on number of electrons, and the number of electrons didn't change. Okay, let's do our first example. So photons with 3.20 electron volts of energy are incident on cesium metal. Incident just means the photons are hitting the cesium metal. Cesium metal has a work function of 2.02 electron volts, resulting in the emission of electrons. Use the law of conservation of energy to find, part A, the kinetic energy of the emitted electrons in electron volts, and part B, the speed of the emitted electrons. So let's do part A first. So remember the formula is this. E, which is the energy of the photon, equals the work function of the metal, and we have to add to that the kinetic energy of the electrons. So here, okay, remember E is for the photon, W is for the metal, and EK is for the electrons. So here I'm supposed to be finding kinetic energy. So I can just rearrange the formula here to E minus W. And so E is the amount of energy that the photons have. So that's 3.20. And W is the work function, which is 2.02. Make sure you're working in consistent units. So if you're going to work in electron volts for the work function, you also need to be working in electron volts for the kinetic energy. And this gives us kinetic energy for the photons of, kinetic energy of the electrons of 1.18 electron volts. So that's the answer for part A. And then for part B, where we're supposed to be finding the speed of the emitted electrons, we're going to use this formula here. EK equals 1/2 mv squared. Now, when we do this, though, whenever you're finding speed from kinetic energy, you always have to work in joules. So what we're going to do is we're going to convert 1.18 electron volts to joules before we do anything else. So if you look on your formula sheet, you're going to find out that in every 1 electron volt, there's 1.60 times 10 to the negative 19 joules. So if we do that calculation, we find out that the kinetic energy in joules is 1.888 times 10 to the negative 19 joules. So then now we can go ahead and we can actually calculate the speed. So rearranging the kinetic energy formula for speed, we get 2ek over m under a square root. So we're going to have 2 times 1.888 times 10 to the negative 19 joules over the mass. Now here, this is kinetic energy of an electron. So it's the mass of an electron, which remember you can find that on your formula sheet. And so the speed here is going to be a rather large number, so we'll write it in scientific notation. So for my answer to 3 significant digits, I get 6.44 times 10 to the power of 5. Okay, next one. So a photon with a frequency of 8.2 times 10 to the 14 hertz contacts the photoelectric surface of a metal having a work function of 4.4 times 10 to the negative 19 joules. Determine the kinetic energy of the ejected photoelectron. So a photoelectron is just an electron. This is just a fancy way of saying photons are hitting a metal, electrons are being freed, find the kinetic energy of those electrons. So if we have the same formula as a minute ago, E for the photon equals W for the metal plus EK for the electron, we can rearrange for kinetic energy, just like before. So kinetic energy is E minus W. Now, we know the work function of the metal. Okay, it's this number, 4.4 times 10 to the negative 19 joules. But we don't know the energy of the photons. But that's okay because we can calculate it. So we have E equals HF. Now, because the work function is in joules here, I'm going to use the version of Planck's constant, which is in joules as well. So that's 6.63 times 10 to the negative 34 joules seconds. And the frequency here is 8.2 times 10 to the 14 hertz. Now remember, hertz can be written 1 over seconds. So what's going to happen is the seconds cancel out, leaving me with something in joules. So I'm just going to calculate what it is. So 6.63 times 10 to the negative 34 times 8.2 times 10 to the 14. This tells me that the energy for one single photon is 8.4366 times 10 to the power of negative 19 joules. So now, all I have to do is plug everything back into this formula that I wrote down at the beginning. So E is 5.4366 times 10 to the negative 19 joules. And we're subtracting from that the value for W, which is 4.4 times 10 to the negative 19 joules. And we want everything to 2 significant digits here. So after rounding to 2 significant digits, I find that EK is 1.0 times 10 to the negative 19 joules. Okay, and last one for today. So a graph of kinetic energy as a function of frequency for a photoelectric experiment is shown. Just have to draw that still. So we have kinetic energy, and we have frequency here. And then it says identify the slope, the Y-intercept, and the X-intercept. Okay, well, we know that at some frequencies, the metal does not release electrons, right? It's only once you hit the threshold frequency that we start to actually release electrons. So our graph's going to start from there. Okay, and what we know is as the frequency of the light goes up, the kinetic energy goes up as well. Now, I can trace this line back to find out where the Y-intercept is. So right here is the Y-intercept, which is called B. And what we need to do is we need to actually explain, okay, what does the slope of this graph represent? What does the Y-intercept represent? And what does the X-intercept represent? So the X-intercept is just the threshold frequency, okay? X-intercept is where the graph crosses the x-axis, which is right here. I'm making it thicker. That's the threshold frequency. To figure out the slope and the Y-intercept, we have to match a formula to y equals sx plus b. So what we'll do is we'll write down the formula. So same formula as before, I just wrote it in a different order. So E equals EK plus W. And in order to match a formula to y equals sx plus b, you need to isolate for y. So here, EK is what's on the y-axis. So I'm going to take my formula that I just wrote down, and I'm going to isolate it for EK. Now, in the formula, okay, we have frequency, and so or in the graph, I should say, we have frequency. So I need to make frequency show up in this formula. So I'm going to rewrite it like this. EK equals HF minus W. Now, my end goal here eventually is to match this equation to y equals sx plus b. Notice how there's a plus sign in there? Again, I need my formula to match that. My formula right now has a minus sign. So I'm just going to rewrite this like this. EK equals HF plus negative W. And now, look what I can do. So now I can say, okay, EK is Y, F is X, whatever's being added to the formula is B, and whatever's multiplying X is the slope. So that means for this graph, the slope of it is going to be equal to Planck's constant. And down here, we have B. So let's just say, just for example, let's say that B was equal to -5 electron volts. I know it's going to be negative because it's underneath, like this is where 0 is. Anything underneath 0 is negative. Since B is equal to the negative of the work function, that means -5 eV is equal to the negative of the work function. And that's the same thing as saying that 5 eV is equal to the work function. So work functions themselves are not negative, but the y-intercept will be negative. But that's okay because the negatives are going to cancel